Evaluate integral 0 to infinity dx upon x raised to 4 plus 1. Replacing variable x by z, we have phi of z equals 1 by z raised to 4 plus 1, whose poles are obtained by equating denominator z raised to 4 plus 1 equals 0. We obtain z equals minus 1 the whole raised to 1 by 4. Minus 1 can be written as cos pi plus I times sin pi, or cos of odd multiple of pi plus I times sin of odd multiple of pi. This is because cos pi equals minus 1 and sin pi equals 0. Similarly, cos of odd multiple of pi equals negative 1 and sin of odd multiple of pi equals 0. Therefore, we have minus 1 the whole raised to 1 by 4 equals cos of odd multiple of pi plus I times sin of odd multiple of pi the whole raised to 1 by 4. Using De Moivre's theorem, we have cos theta plus I sin theta the whole raised to n equals cos n theta plus I times n theta. Thus, we have cos 2n plus 1 pi plus I times sin 2n plus 1 pi the whole raised to 1 by 4 equals cos of 2n plus 1 pi by 4 plus I times sin 2n plus 1 pi by 4, where n equals 0, 1, 2 and 3. Now we will find out particular values for z for n equals 0, 1, 2 and 3, which are the 4 poles of the function phi of z. At n equals 0, we have z equals cos pi by 4 plus I times sin pi by 4, that is 1 by root 2 plus I by root 2. Here, real part of z and imaginary part of z are both positive, and hence this value of z lies in the first quadrant, that is in the upper half plane. For n equals 1, we have z equals cos 3 pi by 4 plus I times sin 3 pi by 4, that is negative 1 by root 2 plus I by root 2. Here, real part of z is negative and imaginary part of z is positive, and hence this value of z lies in the second quadrant, that is in the upper half plane. For n equals 2, we have z equals cos pi plus pi by 4 plus I times sin pi plus pi by 4, which equals negative 1 by root 2 minus I by root 2. We have for n equals 2, the value of z lies in the third quadrant because real part of z and imaginary part of z are both negative. For n equals 3, we have z equals cos of 2 pi minus pi by 4 plus I times sin 2 pi minus pi by 4, which equals 1 by root 2 minus I by root 2. Since real part of z is positive and imaginary part of z is negative, we have this particular value of z lies in the fourth quadrant. N equals 2 and n equals 3 gives value of z lying in the lower half plane. We identified poles given by points n equals 0 and n equals 1. Only these two poles lie in the upper half plane, and we can rewrite this pole z equals cos pi by 4 plus I sin pi by 4 as e raised to I pi by 4 using Euler's identity. Similarly, by using the same Euler's identity, we can rewrite this particular pole z equals cos 3 pi by 4 plus I times sin 3 pi by 4 as z equals e raised to 3 I pi by 4. It's enough to evaluate residues of these poles which lie in the upper half plane. Residue of phi of z at z equals e raised to I pi by 4 is obtained as limit z tends to e raised to I pi by 4 applied on z minus e raised to I pi by 4 upon z raised to 4 plus 1. On direct application of limits, we have 0 by 0 indeterminate form here, and hence we make use of L'Hospital's rule. Derivative of numerator is 1 and derivative of denominator with respect to z is obtained as 4z cube. To this expression, now we apply the limit z tends to e raised to I pi by 4, and we get the value as 1 by 4 into e raised to negative I 3 pi by 4. Following these similar steps, we have residue for f phi of z at z equals e raised to I 3 pi by 4 obtained as 1 by 4 times e raised to negative 9I pi by 4. Since we are asked to evaluate integral 0 to infinity dx upon x raised to 4 plus 1, which in turn equals 1 by 2 times integral negative infinity to infinity dx upon x raised to 4 plus 1, and since we know integral negative infinity to infinity dx upon x raised to 4 plus 1 equals 2 pi I times sum of residues of poles of phi of z lying in the upper half plane, we have the required integral has the value 1 by 2 times 2 pi I into sum of residues of poles in the upper half plane. Here x ranges from 0 to infinity, and here x range from negative infinity to infinity. That's why 0 to infinity this integral equals half times this integral's value in the range negative infinity to infinity. We have 2 and 2 gets cancelled, and the given integral has the value pi I times sum of residues of poles lying in the upper half plane. that is pi I times 1 by 4 e raised to negative 3 I pi by 4 plus 1 by 4 e raised to negative 9 I pi by 4. We can take 1 by 4 common outside and our integral reduces to have this value. Here we again used Euler's identity by which we could replace e raised to negative 3 I pi by 4 equals cos 3 pi by 4 minus I sin 3 pi by 4, and by Euler's identity itself we have e raised to negative 9 I pi by 4 equals cos 9 pi by 4 minus I times sin 9 pi by 4. We have cos 3 pi by 4 equals cos of pi minus pi by 4, and which equals negative 1 by root 2. Sin 3 pi by 4 equals sin pi minus pi by 4, which equals 1 by root 2. Cos 9 pi by 4 equals cos 2 pi plus pi by 4, which equals 1 by root 2. Sin 9 pi by 4 equals sin of 2 pi plus pi by 4, which equals 1 by root 2. Thus we have integral 0 to infinity dx upon x raised to 4 plus 1 obtained as this value. After simplification we obtain the value equals pi root 2 upon 4.